So what we're looking at here is the motor effect topic. So this is in section 6, part B. So the first thing we're going to look at is magnetic field of current. Okay, so if you connect up a wire to a cell, this would create a current that will go through the wire, and it'll be going down this direction in our sort of cross section of a wire we have here, like a bigger version. And what you'll get around this will be a magnetic field that goes in a circular pattern. Now this is perpendicular to the wire, and it goes around like that. A couple of things to note is the field lines get further apart as you head out. So further apart, okay, as you head out. Now, this is sort of all the way along the wire, so you can think about it like a tube. So like a tube at this sort of depth going along, and this is sort of like a slice of that. And so you can see on this image over here that we have our magnetic field B. So that's the symbol for the magnetic field B, okay, going around the wire where the current is going up the wire. Now to find out the direction of the magnetic field, in other words, if I put a north pole here, the direction of the arrow show that the north pole will head off in this direction. We'll feel a force in that direction. To find that direction, we need to use a right-hand grip rule. So we put our thumb up in the direction of the current, and then we wrap our fingers around the wire in the direction of the magnetic field, okay? So in this case, we're going around the back of the wire and around the front, and that's what our fingers show. So if the current goes the other way, then the current will go, so the magnetic field will go around the other way around the wire. So what we could do is also look at it, well, what happens if you don't have like the 3D sort of picture? Another way of showing it is by using a cross and a dot for into and out of a page. So if we had a piece of paper like this, and we had a wire going down through that paper, and let's say the current was going down into this page, then we represent that with a cross, okay? So there's a cross as it hits the page. And so that's seen up here. So this one is into the page and a dot is out of the page. And a way of thinking about that would be like if you had an arrow, okay, if it's going towards you, you would see the point. So it's coming out. And if it's going away from you, you'll see the feathers, okay, so the cross going away. And you just use the same sort of right-hand grip rule. So in this case here, a dot means it's coming out of the page, so you'll hold your thumb up so you see the end of your thumb, and then you wrap your fingers around the wire in that direction so that it shows that the magnetic field is going around like this. Okay, we always use our right hand. How can you make that feel stronger? Well, you just increase the current. Okay, and remember the field lines spread out as you go further out because they get weaker. Next thing we'll look at will be the magnetic field of a solenoid. So a solenoid is a coil of wire. So you can see in this picture here, it's a coil of wire, and this one. But the coil, you can imagine, is just being many pieces of wire coming in or out of a card. So let's say you have your coil, just goes like this, and what I've done is I've sliced it through the middle. And that's what we've got here. Okay, it's sort of like a slice through the middle of the solenoid. And the current at this point here is coming out of the page, whereas this one's into the page. So you can imagine that it sort of goes into the page here, around the back, out of the page, and then back over again. Okay, so it sort of goes around the back and over the top. Okay, and that's sort of how it's set up. But what it shows, this sort of diagram, it shows that the magnetic field around these sort of cross sections all go the same way in the middle. They're all going this way in the middle. And what happens there is they all sort of join up, and you basically get the same sort of magnetic field that you would get if you had a bar magnet. Okay. Now, how do you find the direction of the north pole of this thing? Right-hand grip rule again. Before, we had a single wire, so we had a single current. So that's why we used our thumb for the current. But now, we're going to use our fingers for the current because there are many currents. In this case, the current is going up the front of the solenoid. So you can see the current coming up the front of the solenoid. And you wrap your fingers over the solenoid in the direction the current goes around the solenoid, and your thumb then points to north. Okay. Now you notice that the solenoid is stronger in the middle, as where the field lines are much closer together, and a lot weaker on the outside. Okay, and the good thing about solenoids is they create a uniform field in the middle there. Now, how can you increase the strength? So you can increase the strength by having a higher current. Zoom out a bit. You can have a higher current. You could have more coils, and that will help make the strength a lot stronger. You can also put in, remember, an iron core, which will turn into a magnet in its own right. And basically sort of you then have a magnet inside a solenoid. So you have a magnet and the solenoid, and that will then make it stronger. And remember, we use iron because it's temporary. Okay, if you use steel, it will stay magnetized and wouldn't be able to turn off if it was an electromagnet. Now remember, changing the current direction will change the field direction. Okay, next thing we'll look at will be a force on a current carrying conductor. So if we set up a simple experiment like this one here, where we have a power supply basically connected to this wire, and you'll get a current flowing in this wire, and it comes along the top. And even better would actually be to have a switch in it. And so when you close the switch, you actually will find the wire would pop up. Okay, so there'd be a bit of motion. So that means there is a force in the upwards direction. So that shows that a current carrying conductor will feel a force in another magnetic field. And we know that will occur because let's say I had a wire going into the page. That will get a magnetic field going around it in this direction. Okay, and then if you put a north pole here, and a south pole here, the field lines would go across like this. They would join up at the bottom, but they're basically going to sort of repel at the top. Okay, and that's why you're going to suddenly get sort of a motion, because we've got an opposing field here, and we've got a in the same direction field there. Okay, and that's going to create an imbalance. So you're going to create motion, and it's basically magnet versus magnet. What do you need to know? You need to know the direction of the motion is going to be, and we use this thing called left-hand Fleming's rule. And if they ask you, it's named after Mr. Fleming, if they ask you, how do you know the direction? Just say, because of left-hand Fleming's, okay? So left-hand Fleming's is you hold up your left hand, okay, and your thumb is going to be the direction of the force. Your first finger is the direction of the magnetic field, which is B. And these fingers, or the second finger, or you could use all the fingers, so all three if you wanted to, that is the direction of the current. Now I like to use FBI, you could use whatever you want, but I basically like to say this is your FBI's gun, Okay, so you can hold it up like a gun. Okay, not that I promote guns, but it's like a gun. And you're the FBI, and you're left-handed. And so F is for force, B is actually the symbol for magnetic field, and I we know is the symbol for current. So you can remember it that way. Now what you've got to do, if we go back up to our first example up here, you have to show your second finger goes along this way. Okay, your second finger goes along that way. Your first finger is going to point in this direction here, and then your thumb points up. Okay, so I'm going to point my fingers here. So these ones here are going to go along the direction of the current. My magnetic field is pointing from left to right for me, and that means the actual force is up. Okay. So that's how we find the direction. Now the other thing you need to find out is, well, how can I increase that force? One, I could increase the current. That will increase the force. Two, I could increase the current. Two, I could increase the number of wires. And you'll see that when we do a motor, what I mean by that. And the third one is increase the magnetic field. Okay, and those are the ways to increase the strength of that effect. Now let's have a look at a practical application of this, and it's called the DC motor. So here is a basic picture of a DC motor. So we've got a north and south pole, and those create a field going from the north to the south. Okay. Then we have a coil of wire. So there's a green coil of wire. It could be on like a pivot at one end and a pivot at the other end. And that means it's free to rotate. Now, if we use left-hand Fleming's, so we've got a current flowing from positive, comes along here, hits this sort of join there and goes along, and then comes along here. And so we've actually got a current this way. So you can actually use your left-hand Fleming's to go, current is these fingers there, my field is left to right, that means my force is up, okay? And then as you go around, the current goes along here. Now the current is not 90 degrees, so there is no force. And then it comes along here and goes this way. Now we've actually changed the current direction. So we're now going the other way, so that means the force is now down. And if you think of having a pivot through the middle, we have got a force and a distance, so we get a thing called moments, okay? So we've got two moments, opposite directions. This thing is going to rotate. So I can actually show you a interactive version of this. So here we got an interactive version. So I'll make this thing run now. So we've just talked about the two forces opposing each other. So if I now make it run, you'll see that it's going to start moving up like that, okay? Now the biggest force is actually when it's 90 degrees because it's got the greatest distance from the middle. As it starts moving up, so the distance is from the middle to the side. As it starts moving up, that distance is decreasing. Now you also notice that as you get towards the top, you see that the connection from the battery to the coil actually will come off this thing. And I'll talk about what that is in a minute. But it's now disconnected, so the current doesn't work. So what actually happens at this point is there is no current flow. Okay? And I'll show you what would happen if there was a current. So let's just take a screenshot of that. And we'll paste it in here. So if there was actually a current flowing, so let's say the current was going this way and this one was this way, the force would be up and the force would be down. They're actually no longer got a distance from the pivot. It's actually straight through like this. There is going to be no, it's not 90 degrees from the distance. Remember, for a moment, distance and force needs to be 90 degrees. In this case, the distance and force are in the same direction. And so that means it's just going to try and stretch the coil. It's not actually going to try and make it rotate. So that means you won't get that rotation anymore. Now, how can you get past this point? Well, what will happen is we're actually moving before the inertia or that momentum will carry it across and make it go to the other side. Okay? Because you'll see that the connection here will then rejoin up. Okay, so let's run it again. You see now we get to a point where the current has actually swapped the way around the wire. Now, why is that? Well, what's happened is as the coils got to the top, this side here, let's color it orange, this side here will move to the top, and so eventually it will be at the top, and then it goes over to the other side. So if the current here was still the same direction in the orange one as it was before, which is this way, then the force is up, and that means you'll no longer keep rotating. Your motor or your coil will continue going this way, get to the top, maybe go across with a bit of momentum, but then it'll feel a force and it'll start going back the other way again. And you basically get to a point where it'll just stand up and be stationary. So what you need to do is actually swap the current direction when it gets to the other side so that it feels a force in the other direction. And that's the key of this little device here. Now that thing is called a split ring commutator. It might not usually look like that. Usually what happens is you actually have your two sort of wires, and they will actually be attached to a ring, like a split ring. So it's actually like you imagine having a circular piece of metal and then cutting it in the middle. Okay, and then what you can have on each side of that is these things called brushes, and they then connect to your cell. And those brushes then just glide along the back of this thing as this thing rotates. So the orange part's going to rotate and eventually go to the other side, and the pink will go to the other side. And that means the current in the coil will keep changing direction every sort of half cycle, okay, half a loop. And that keeps the thing going. So that thing is called a split ring commutator. Split ring commutator. Okay. If it wasn't split and it was just a commutator, which is just two brushes, usually made of graphite or it's just pieces of metal like a comb, if it wasn't split, or if it kept on doing the connection to the same side the whole time, you'd have basically need an AC motor. You need to be able to turn the current round, so you'd have to use an AC current to make it work. Now, how do you make this effect stronger for the motor? What you need to do is basically you could have three things: higher current, a higher magnetic field, a stronger magnetic field, or more loops. Okay, so in the demo, I can actually do that. So in this one, I can make it run. And to make it go faster, I could increase the number of loops. So basically, each one of these gets the force F, so I've now got 3 times the force. I could increase the current, which is increasing the battery voltage, will make the current go higher. Can you see how the wires make the current swap direction? So this one's going towards me, and then it's now going away from me, okay? And I can also increase the magnetic field strength, and then I get my top speed, okay, for this motor. Okay, so that's everything you need to know for this last sort of the motor effect section.